So in the last video we looked at using L'Hopital's rule for something of the form 0 times infinity, and the idea was to rewrite the product as a fraction so it would be in the form of L'Hopital. Today, or in this video, we're looking at indeterminate forms of the type infinity minus infinity. And so let's just do a quick example just to see how this works. Limit as x goes to infinity of the square root of x squared minus 3x plus 1 minus x. Now you might remember we did problems like this before, and we didn't need L'Hopital's rule. And in fact, it's probably better not to use L'Hopital's rule in this case, but we'll see why. Whoops, that's minus. Oops. We're multiplying by the conjugate, remember that? And so in doing that, we make the difference into a fraction, right? And so remember, if you have a minus b times a plus b, you get the a squared minus b squared type rule here. So that's that squared minus x squared, and then divided by the square root of x squared minus 3x plus 1 plus x. Oops, I forgot my limit. Limit as x goes to infinity. Good. Simplify that numerator, and it looks like we have the limit as x goes to infinity of minus 3x plus 1 divided by the square root of x squared minus 3x plus 1 plus x. Good. Now, how do we go from here? Well, you could use L'Hopital's rule here because now we do have an infinity divided by infinity. However, I would recommend not doing that. Why? Because if you take the derivative of the square root, remember what happens? Whoops. Not sure why that went to my web page. Okay. If you, where was I? So if you do take the derivative of a square root, you end up with a square root. And so the L'Hopital's rule doesn't really help in this case. However, do you remember what we did? We divided the numerator and denominator by x. And so then we were able to get our expression that we wanted. And so then we would have 1 minus 3 over x plus 1 over x squared, right? Because when x goes under the radical sign, it becomes a square root of x squared. Good. And now you see that as x goes to infinity, that goes to 0, 0, 0. So you're left with minus 3 divided by the square root of 1 plus 1, and that's going to be minus 3 over 2. Very good. All right. So we did this problem in order to see that sometimes it is better to use the old techniques. You don't want to use L'Hopital's rule all of the time. So don't forget our old techniques. Let's try another one. Example. How would we do the limit as x goes to infinity of, how about the secant minus the tangent? Secant of x, oh, maybe not infinity, pi over 2. Otherwise the limit would not exist here. Pi over 2, and then we'll come in from the right, of secant of x minus the tangent of x. Good. Now, whenever you're dealing with excuse me, fractions like this, a good starting point is always to do a conversion back to sines and cosines. Oh, by the way, what kind of a form do we have here? Should we check that? Secant is what? Secant is 1 over cosine, and tangent is sine over cosine. And so as x approaches pi over 2, 1 over cosine, what does cosine do? Cosine goes to 0, right? And so this will be 1 over 0, so this is going to infinity. And then what is this one doing? Yeah, it's going to do the same kind of thing, right? Because the denominator is going to 0, but the denominator, the numerator is not. The denominator is going to 0, but the numerator is not. Therefore, this is an infinity minus infinity form. And in fact, with these fractions here, you can see what we're going to do. Let's go ahead and make a single fraction out of this. And so that's going to be cosine of x at the bottom and 1 minus sine of x at the top. Gosh darn it. And now, what is the form that we have? In the denominator, we're going to 0, and in the numerator, sine of pi over 2 is equal to 1, so this is going to be going to 0 in the numerator, and so now we can use L'Hopital's rule for this form. Good. Pi over 2 from the right, so that's going to be minus the cosine of x divided by minus the sine of x. We'll be putting some plus signs there. Good. And then what is cosine of pi over 2? That is 0. So this is 0 divided by 1 is where it's going, right? And that is 0. Good. All right. So our indeterminate forms so far, the forms that we've been working with so far, have been 0 over 0, plus or minus infinity over plus or minus infinity, 0 times infinity, and then this last one was infinity minus infinity. And now we want to do one more, and that is either, you could think of it either as like 0 to the 0 power, or infinity to the 0 power, or maybe 1 to the infinity power. Okay, in all of these cases, the same trick is going to be working, where we've got f of x to the g of x power, right? In all of these cases, that we're trying to take the limit. Now, if I have y equals f of x to the g of x power, is there a way I can change the exponentiation into a product? Here's a hint. We use the same trick in differentiation. The trick is to take the log of both sides. The log of y is equal to g of x, well, let me rewrite it as natural log of f of x to the g of x, g of x power, my parentheses wrong, and then the g of x drops down in front. And now the idea here is that you have one function times another function. And so we're back to this rule, right? Where we're multiplying two things together. Good. So what we're going to do then is we're going to take the limit as x approaches a of the natural log of y. And suppose that that limit is actually equal to L. Then what is the original limit going to be? The original limit is, since we took the natural log to start with, we want to exponentiate to end with. So the limit as x approaches a of y is equal to e to the L, right? So once you're finished computing the limit using the log, this is kind of a two-step process, right? Take the logs first, and then once you find this limit, exponentiate to get your answer. Okay, so we'll try this out with an example. How about the limit? The limit as x goes to 0 of x to the x power. Now this is kind of interesting to think about, right? Because as x goes to 0, right, you could think of it two ways. 0 to any power is going to be 0, but any power to the 0 power is 1. So is it 0, or is it 1, or is it some other number? Well, like we said, first thing you want to do is take the limit of the log. And so instead of doing the x to the x, we're going to take the limit of the log. And when I take the limit of the log, that turns the limit into a product. oops, that's 0, x natural log of x. And I think we actually already did that one, didn't we? So just to keep going, that was the natural log of x over 1 over x. You remember that? And then when we use L'Hopital's rule, we get 1 over x divided by minus 1 over x squared. Take the limit as x goes to 0. And so that ended up being the limit as x goes to 0. We want to invert and multiply. That's 1 over x times minus x squared over 1. You remember that now? Limit as x goes to 0 of minus x equals 0. Good. But our answer is not 0. The answer is the limit as x goes to 0 of x to the x is equal to e to the 0 power, which is 1. Good. All right. And so let's see, do we have time for one more? Let's try one more. So how about the limit as x goes to infinity of 1 plus 3 over x to the x? All right. So if we take a look at it, as x goes to infinity, this term right here goes to 0, so that's going to 1. And so this is a 1 to infinity form, right? Good. So what we want to do, step 1, is to take the limit of the log. And so we take the limit as x goes to infinity of the logarithm of this expression. And the reason we do that, again, is because that changes things into the product, which is x times the log 1 plus 3 over x. Good. And now this limit we can convert into a fraction like we did before. Natural log of 1 plus 3 over x divided by 1 over x, right? And now we can use L'Hopital's rule. Limit as x goes to infinity. This is going to be 1 over 1 plus 3 over x times the derivative of 3 over x is minus 3 over x squared. And then divided by minus 1 over x squared, right? But then if you invert and multiply, you get that expression. The x squareds cancel, minus cancels, so you end up with the limit as x goes to infinity of 3 over 1 plus 3 over x. Good. And so that's going to go to 3. But that's not the end, right? So that means that the limit as x goes to infinity of 1 plus 3 over x to the x power is equal to e to the 3 power. Good. And that's how it's done. And so just as a quick summary now, we've covered several possibilities, right? We've covered 0 over 0, plus or minus infinity over plus or minus infinity, 0 times infinity, infinity minus infinity, and then we have all these products, or these f of x to the g of x power, where we have 0 to the 0, 1 to the infinity. What else did we have? Those are the only two we've looked at examples of, but there are some other possibilities there. Infinity to the 0 power, I guess, is the one that I missed. We haven't looked at that one yet, but we could do an infinity to the 0 power. Good. So in the next video, we're going to summarize this again. So we'll keep these possibilities open here, and then we're also going to look at some special cases where we have to be a little bit careful. All right, I'll see you then.